All right, I think we're live. Hello, everyone. Good morning, afternoon, evening, wherever you're tuning in from. I am Apurva, and I am a senior AI developer advocate here at MongoDB. Thank you so much for being here today and for taking the time to come here and learn something cool with me. In today's webinar, we are going to be building a RAG system with something called self-querying retrieval, and we'll see how to introduce controllability into the system using LangGraph and reliability using structured outputs. We also wrote a detailed tutorial about this a while ago, which is hopefully linked in the video description or will be, so feel free to check that out in your free time. So let's first understand what self-querying retrieval is and some use cases for it. Let's look at this scenario where you're trying to build a RAG-based financial investment assistant. So you have built your knowledge base by chunking up and embedding publicly available financial reports for a bunch of Fortune 500 companies, but you're facing this problem where you don't seem to be getting the right responses from your investment assistant. So what might be the problem here? The problem is that these reports have very similar language covering similar topics, and they often refer to any given company as the company throughout the document. So when you chunk up these documents, you lose the context of the company and also perhaps the fiscal year if that's something that's important to you. So now say you tried to get the earnings summary for MongoDB for 2023, you might end up retrieving chunks from a document for Goldman Sachs or Walmart or from a financial report for a different fiscal year. Just going to check one thing real quick. Okay. So how do you fix this? One way to fix this is by extracting the right metadata from your documents while ingesting them in your vector database. So you have to be thinking about this at the data processing and ingestion phase itself. So the way to do is, so then once you've extracted the right metadata and ingested your documents into the database, given a natural language query, self-querying retrieval is the process of first extracting specific metadata from it, constructing structured filters using the extracted metadata, and finally applying them as pre-filters during vector search to retrieve documents from the knowledge base. So in the case of our financial assistant, given a user query, you would first extract any company names and year ranges from it, create a filter for these extracted companies and time ranges, and then apply these filters as pre-filters during vector search. So this way you can be sure that you're retrieving documents corresponding to the right company and fiscal year if the user specifies these in their query. So essentially, use metadata filtering and self-querying retrieval whenever you have a task where you would benefit from narrowing down your search based on very specific and structured criteria. Let's briefly talk about the tools we used to build our self-querying RAG system, and you'll actually be seeing a live code walkthrough of this in just a little bit. But yeah, let's quickly talk about those tools, right? So we first have unstructured. Unstructured allows you to extract different elements such as text, images, tables from your documents using specialized machine learning models. It also allows you to extract metadata from your documents, which is the first step to be able to do self-querying retrieval. They also have support for an exhaustive list of file types, data sources, and destinations. So like not just PDFs, they have like EPUBs, CSVs, PowerPoint, and data sources like S3, Google Cloud Storage, you name it, and then destinations such as MongoDB and other databases. And finally, you can write custom pipelines to really process your data based on whatever the needs of your application are. We'll also be using MongoDB as the vector database for our RAG application. The reason being, well, I work at MongoDB, but that's just part of it. The real reason is we are even able to combine pre-filters with vector search because MongoDB Atlas provides you with an integrated platform for your operational and vector data, and both of these are queryable using a unified MongoDB query API. Apart from that, since your operational and vector data reside in the same collection, your data is automatically synchronized with vector indexes that you might create on the collection. And finally, it's a fully managed service, which means you don't need to worry about maintaining infrastructure. And instead, you can focus on building cool applications such as these. And finally, there's search nodes. So while there's like a unified user experience, unified experience for the user, at the back end, we scale these compute intensive search workloads independently of the operational database so they don't interfere with each other. And finally, the whole thing we are discussing today is a part of it is building controllability into your LLM applications. And the way we've done it here is using LangGraph, which is a low-level agent orchestration framework from LangChain. The idea here is to orchestrate LLM applications as graphs, which means you get full control over your application's workflows. You can implement things like loops, conditional edges, and you can also pause and resume graph execution, which means you can do things like human in the loop to get human feedback and then continue from there. And while this is mainly targeted towards agents, I think, and I'll show you how you can orchestrate any LLM application in this manner to gain full control over the state and flow of your applications. So with that, let's look at some code. Actually, let me see if there's any questions. But okay, I think Pedro's mentioned that I'll answer questions after. Yeah, so towards the end, we'll have about 15 minutes for questions. So feel free to ask me questions then. Cool. Let's see. Okay, so for the first part, well, let me back up a little bit. We are going to be building that financial investment assistant that I was talking to you about. The goal of the assistant is to provide investors information about financial standing of companies they're interested in. We'll use 10K filings from Fortune 500 companies as the source of information for our assistant. And the reports look something like this, and they offer a deep dive into the company's financial history. So as you can see, these documents are super long, each one about like 200 something pages. And they all look pretty similar. So they start sort of like this, and then they have pretty similar information. So as you can imagine, we might lose some context, important context, when we are chunking and then embedding these documents. So the first thing we are going to do is chunk, embed, and also extract metadata from these documents using unstructured and write them to a MongoDB collection. And it takes a while to run this end-to-end processing pipeline. So for the first section, we'll just walk through the code, and then we'll actually get hands-on for the second half. So this is the notebook. It's on our GitHub. That should be linked in the video description as well. If you've looked at the article, it should be linked in the article as well. But basically, what we are doing is first things first, installing required libraries. So we are using LangGraph here, OpenAI, LLMs and embedding models, PyMongo, which is the Python driver for MongoDB to connect to MongoDB databases and collections. Sentence transformers, which is a Python package that allows you to use open source language models from Hugging Face, and unstructured ingest, which is the Python package for data processing using unstructured. So the next thing after importing, we set up some prerequisites. So if we were actually running the pipeline, you would need an unstructured API key and the URL to your unstructured server, I believe. Then a set of AWS authentication credentials, because here for this tutorial, we had used the source of our information as S3, but if you're using Google, then you would obtain the appropriate authentication credentials. And then we want to connect to a MongoDB database and collection, because that's going to be the destination for our process data. So you would set that up first. And then your OpenAI credentials, because that's the LLM we are using, but that'll come later on. You don't immediately need to do that. But essentially, this is what the data processing looks like. So the first stage is partitioning, chunking, and embedding these documents here. They're just a bunch of PDF files that are sitting in an S3 bucket for the purpose of this tutorial. The way to do this using unstructured is using something called pipelines. And pipelines are nothing but a series of data processing steps. And steps in unstructured pipelines is a series of configs. And this is what they look like. So in this case, we are going to be writing, well, temporarily writing the embedded and chunk data to a local folder. So we'll set the working directory first. And then here's the actual pipeline that's going to do the partitioning, chunking, and embedding of the data. So first off, we have an S3 indexer config to give the pipeline information about like where our data is sitting. So the S3 URI and then the connection credentials for S3. Then we have the partitioner config to configure the partitioning settings. And partitioning here is essentially extracting the different components from the document. So any text elements, images, tables. So just setting those configurations here. So we are saying split PDF, yes, and any error handling and a concurrency level to like run to parallelly process multiple documents. What else? And we are using this high-res strategy, which is like the most powerful and all-purpose strategy that you can use to process documents, partition documents using unstructured. Then there's a chunker config, which is specifying the chunking parameters. So we are saying we want no more than 1,500 characters in a chunk, and we also want some chunk overlap. And we usually recommend like 15 to 20%. I think here we've done 10, but 10 to 20% of the chunk size as the chunk overlap. And the overlap essentially accounts for continuing context over the chunk boundaries. So if you didn't do that, then you'd have like disjoint chunks. But if you have overlap, then you're going to have like continuity moving from one chunk to the next. And then we also have the embedder config, which is the embedding settings. So here we are saying we want to use a model from Hugging Face, and then we've set this which model to use up here. And that's the model we want to use for embedding. And finally, we are saying where to upload the processed documents. So as I mentioned, we are temporarily writing these documents to a local directory. So that's what we are doing. And then we would run this pipeline to run this whole pipeline. So once we've done that, the next thing we want to do is extract custom metadata from these processed documents. And we want to extract two things here. We want to extract the company name and the fiscal year. So if you look at these documents, it's pretty standard where the company name appears. So we are going to use a simple regular expression to extract both the company names and fiscal year. So as you can see here, we are using this regular expression, and this is how we would extract the fiscal year. And for company name, it can appear in one of two places. This is one of them, like this Walmart Inc. here. And then there's another place a bit deeper into the document where in some documents, that's where it appears. So we are using either the first most obvious one or checking for this other regular expression. So we've written those two functions. And then we are going to take the intermediate documents that we just wrote, and we are going to extract custom metadata that we are talking about from all of those documents and writing them to another intermediate directory. So then once you've done that, the final step is to actually write those processed documents to MongoDB. So if you look here, this the second pipeline looks pretty similar to what we were doing previously, and that is the case. So in this case, the only thing that's really changing is we are saying instead of the destination being a local directory, this time we want the destination to be a MongoDB collection, because that's where we eventually want our data to end up. So then we would run this pipeline, and then we pretty much have all our data processed and ready to go to actually build our self-querying RAG application. So since we haven't run this pipeline, I'm at least going to show you what those documents would look like once they are processed and sitting in a MongoDB collection. So here, I've already run that pipeline a few weeks ago, and this is what the documents look like in MongoDB. So you have the embeddings field, and then you have the metadata field, which has some automated metadata that was extracted by unstructured. But then here's this custom metadata field, which is the custom company and year metadata that we extracted using the regular expressions from each document. And this is what's really important, and this is what we are going to use to build filters off of. Cool. So that's like just the code walkthrough, but now we are going to do a little bit of live coding and pray that everything goes smoothly. But I'm going to take a pause to just see if there's any questions so far. Otherwise, it's just going to be a lot of things to process towards the end. So going back here real quick. Let's see. Actually, there was someone who had questions at the very beginning. If you want to ask those right now, let's do that. Can we get the video link after the event? So yeah, this video is going to be available on LinkedIn and YouTube after the live stream itself. So yeah, it should, in theory, be available forever. Anaya, thank you so much for taking the time. Anaya is my work bestie, so I'm happy to see a familiar face. Let's see if there's more questions coming in. Okay, I don't see any questions coming in right away, so I'm going to move on to the live coding portion, and I'll come back and check for questions after that. Okay, so quick status check, right? So far we have our documents in MongoDB. We've done all the pre-processing, and now we are ready to actually orchestrate our RAG application. So I've done a few things already here. I went ahead and installed the libraries that we need and the prerequisites, which is like connecting to MongoDB, making sure the connection went through without any errors, setting my OpenAI key, and then I think we are ready to roll. So the first thing we want to do, set the embedding model. We are going to need this for vector search later on. Then setting the completion model, which is the LLM that we want to use for generation. And then, as mentioned, we'll use LangGraph to orchestrate our self-querying RAG system as a graph. So the nodes of the graph are functions or tools to perform specific tasks, and the edges in the graph define nodes, routes between nodes. And these can be fixed, conditional, or even cyclic. And each graph has a state, which is a shared data structure that all nodes can access and make updates to. And you can define custom attributes within the state depending on what parameters you want to track across the nodes of the graph. So let's first go ahead and define that graph state. Imports. And then here's that graph state. So in my graph, I want to track the question as it comes through, because like every node in the graph will very likely want to access the question. Then as I extract metadata from the queries, I'll write that to the graph state. And then I'm going to be building those pre-filters using the metadata extracted. So I want to track that in the state as well. And then once we perform that vector search to retrieve documents for RAG, we are going to add that to the context attribute of the graph state. And then later on, we'll see how to persist chat history for multiple back and forth interactions with our RAG application. And we want to track that in the state as well. So let's go ahead, define that. And the next thing we want to do is add the graph nodes. And each node updates one or more attributes in the graph state with its return value after it executes. And we'll see how that happens. But our assistant has 4 nodes. The first node is for metadata extraction. And what that's going to do is extract metadata from a natural language query. Then we have a filter generation node, which is going to generate a MongoDB query API filter definition from that extracted metadata. Then we have a node to perform vector search. That's going to retrieve documents from MongoDB using semantic search. And then we have an answer generation node, which is to generate the answer to the question. So first, let's write out that metadata extraction node. So extracting metadata from natural language is not an easy task. So in our case, for example, the company names extracted from the query need to exactly match the names that we have in our database here. Otherwise, the filters will not really match any of the records in our database. Users might also use phrases such as in the past year, or past 3 years, which we would need to translate to actual numbers and date ranges. So we are going to use an LLM to do this, but as you can imagine, this poses a reliability issue, right? So to tackle these, we are going to use OpenAI structured outputs feature, which means the LLM will conform to a specified output schema while returning the outputs. And this is how you incorporate that reliability into your LLM application. So let's do that. Imports, and then I'm going to specify the list of companies in my database. And then I'm going to define a pydantic model. So a pydantic model is basically a class with attributes and their types. So when data is passed through this model, it automatically gets validated according to the type specified. So in this case, I've defined a pydantic model called metadata, and the attributes that I want are company and year. I'm saying company needs to be a list of strings and year needs to be a list of, well, it's supposed to be ints. I don't know why I have string there, but the year needs to be a list of strings. I think this should be strings and this needs to be int. Okay. List of company names. Okay, let's run that. And then we are actually going to define the metadata extraction node. So as I said, we are going to be using an LLM to do this. So the first thing we want to do, so as you can see here, we pass in this graph state to each node in the graph. And in this case, we are going to read the question from the graph state, and we are going to use an LLM to actually extract the metadata. The way we do that is using a prompt. So we are providing it information on how to extract the companies. We say only adhere to this list of company names and some instructions on how to extract the start and end year. And then just to show you, like the reason I use like the OpenAI APIs directly is to show you that you don't necessarily need to use LangChain to be able to use LangGraph. You can have essentially any Python code and any Python function as the nodes for the graph in LangGraph. So yeah, once I have the prompt, just going to make a call to the OpenAI API. And the thing to notice here is that I've set this parameter called response format to the pydantic model we described here. And that's how we are going to get those structured outputs back from OpenAI. And then I'm doing a little more pre-processing to just match the format of that output object to the field names that I have in my MongoDB document. So in my documents, the company name is under metadata.custom metadata.company and year is under this field. So just trying to make that process as reliable and simpler as possible. Okay, we run that. So then once we have extracted the metadata, the next step is to create the MongoDB query API filter definition. So to do this, again, we use an LLM with a prompt containing rules to create the filters. And it's a small and finite set of rules with no real ambiguity. So we have seen it perform pretty well. And here we'll use another method of imposing structured outputs, which is just JSON outputs. We don't really need a specific pydantic object here. We just need the filters to be in JSON format. So here's our prompt. And this time we are passing in the state again, but we are going to be extracting the metadata from the state because that's what we are going to use to build the filters. So again, pass that prompt to make an OpenAI API call. But this time you see the response format parameter is set to type JSON object, which is to tell OpenAI, like, I need the output back as a JSON object. And then we are writing the filter back to the graph state, this time writing to the filter attribute. Run that. So at this point, we'll have the filter definition. The next thing is to use these as pre-filters for vector search. Go ahead and do that. Well, just imports here first. Okay. Yeah, so just loading my embedding model, specifying which collection to perform vector search against, and then the vector search index name. So in MongoDB, if you want to perform vector search, the first thing you need to do is create a vector search index. It's just settings to build the HNSW graph, which is the algorithm that we use for approximate nearest neighbor search. And it just specifies, actually, let me just show you what that looks like. Let's look at that. So it just specifies the number of dimensions in your embeddings, the path to the embeddings field, what similarity metric, embedding similarity metric you want to use for getting nearest neighbors. In this case, we want to use cosine similarity. And then if you want to do any pre-filtering, then you also want to index the filter field. So in our case, we want to index the company and year field. So going back here. Okay. So I've already created my vector search index, but just to show you, if you wanted to do that programmatically, you would create that index definition here and then use the create search index method from the PyMongo library and pass the index definition to the model parameter. If you run this, this will programmatically create that vector search index. And next, we want to define the next node in our graph, which is going to perform vector search. So in this case, we want to read the question from the graph state, and we want to read the filter. So once we do that, the first thing we want to do is generate an embedding for the user question that's how we are going to do semantic search. And then we define that vector search pipeline. So in MongoDB, the way vector search works is it's part of our aggregation framework. And aggregation pipelines in MongoDB are nothing but a series of data processing stages. So vector search is one of those stages. But the one thing to remember is it's always the first stage in the aggregation pipeline. So you first get a bunch of results using vector search, and then you can do any other pre-processing, post-processing steps on those search results. So this is how you would define the vector search stage. It's this operator called $vector search. You specify the index to use, the path to the embeddings field in your documents, the query vector, which is the embedded version of the user query, and the number of candidates to consider while performing the approximate nearest neighbor search, and the limit, which specifies how many most relevant documents we want to get back from the vector search. And then here's that pre-filter. So at this point, we are going to use that filter consisting of the company and year range filters and use that as a pre-filter for vector search. And then we are using the project operator, which essentially just passes or extracts a subset of fields from the vector search results and returns that as output. So in this case, we are saying, I just want the text from the documents and the vector search scores. And then what it does is runs that pipeline that we defined here. And the thing I wanted to show you is what we are doing with the scores, right? So the reason we output the scores is you can do some post-filtering using the scores as well. So in this case, I'm saying I only want documents with a score greater than 0.8. So you're further improving the relevance of the documents being returned for RAG, and by only returning the most relevant documents from the vector search. And then doing some very simple formatting, which in this case is converting that list of documents to a new line separated string, and then writing that context to the context attribute of the graph state. So that's what this node is doing. And that brings us to the final node. Let's see. So the final node we want to create is a node to actually generate the final answer by passing the question and retrieve documents to an LLM. So defining that, in this case, we'll read the question from the graph state, the retrieved context, and if there's any chat history from the conversation, we want to read that as well. And then in this case, our system prompt is just saying, if you don't find any relevant context to answer the question, then just say you don't know. This is just a simple way to get the LLM to not hallucinate. Like there could be other issues, but it's just a simple technique that sometimes works well. And then again, just making that call to the OpenAI API and parsing out the return answer. And this time we want to write that answer to the memory attribute of the graph state because you want to build upon that chat history. Do that. So now we've defined the nodes for the graph, right? And the next step to do is connect these nodes because we actually want to define how inputs flow from one node to the next. So most of these nodes are going to be connected by fixed edges, except if we don't extract any metadata from the user query, we can directly skip to the filter generation step, and we can skip the filter generation step and go directly to vector search. So for that one case, we are going to add a conditional edge. And that's, again, a Python function. This time we'll read, in that function, we'll read the metadata attribute of the graph state, and we'll check whether or not metadata was extracted. If it was not extracted, we'll return a string called vector search. And if it was extracted, then we'll return a string that says generate filter. And we'll see how to use these outputs to build this condition into the flow of our graph. So now we've defined our nodes, we've defined that conditional edge. The final step is to connect the nodes and edges to build the full end-to-end flow of our graph. So the first thing to do is define the graph and parameterize it with the graph state that we previously defined. And then we also create this memory saver, which is something called a check pointer. And what these do is persist the graph state between interactions in LangGraph. And this is how our system is going to persist that chat history going from one interaction to the next. And then we are going to finally add the nodes and edges to the graph. So first, just add all the nodes. Add edge is to add any fixed edges. And then here's how you add conditional edges. So we are saying from the extract metadata node, do this check metadata check. And then if the output of that check is vector search, then skip to the vector search node. And if the output is the string generate filter, then skip to the generate filter node. And then here's more fixed edges between the other nodes. Also notice the start and end. These are special nodes to indicate which node to call first, which is start, and which nodes have no additional actions, which is the end node. Yeah, that's pretty much the structure of our graph. So let's run that. And you can also visualize your graph to make sure that everything's connected the way you want it to be. So we start, first extract metadata. If no metadata was extracted, then skip to vector search. If it was, then generate filter and then go to vector search. After vector search, we go to generate answer and then we end. So that looks good to me. The final thing is to actually execute the graph and to make sure that things are working, right? So we define this method, this function here. It takes two parameters, the thread ID and the question. So thread IDs are unique IDs assigned to memory checkpoints in LangGraph, and each checkpoint has a separate state. So it's just a way for LangGraph to distinguish between different conversations. So the first thing we want to do is add the question to the question and memory attributes of the graph. So this is pretty straightforward. Why are we adding it to memory? It's just like adding incrementally to build that conversational history. And we pass that thread ID as a configurable. It's just LangGraph stuff. And then we are going to stream outputs as they come and pass through our graph. So streaming the outputs from our graph, and we are going to print what node we are at and the value at that node. And finally, we are going to print the final answer, which we are going to obtain from the last message that we added to our memory, which is always going to be the latest answer from the LLM. Okay, so showtime. Let's see if this works. So I'm saying execute graph, giving it a thread ID of 1. Actually, I may have, let's use a random ID, just so I'm not interfering with previous runs and we are starting like a fresh conversation. And this is my question. Give me the sales summary for Walmart for 2023. So let's see what happens here. Okay. Oops. Okay, it's a lot to read through, but essentially it passed through the extract metadata node, and this is what it extracted. Extracted the company to be Walmart Inc. and the year to 2023. And then it passed through the generate filter. And this is what that MongoDB query API filter definition looks like. So we're using the $EQ operator saying the company name should equal Walmart Inc. and the metadata year field should equal 2023. And then it's performing that vector search using those filters. And finally, it gave us the final answer. Now let's see if it's actually using chat message history, right, to make sure that our memory functionality is working. So give it the same thread ID, and let's ask it, what did I just ask you? If it's actually taking history into account, then it should tell me what previous question I just asked it. Okay, so here's that conditional edge working, right? So it didn't extract any metadata this time because there's no real metadata to extract from this query. And you can see the decision here was to skip directly to vector search. So it skipped to vector search, but it didn't really retrieve any relevant context from our knowledge base. But it had that memory. It read from the memory attribute of our graph, and it found that I had asked it about the sales summary for Walmart, and that was essentially the only context it had for this question. So it finally answered me saying I asked for the sales summary for Walmart for 2023. And the last thing we want to check is if it's a completely irrelevant question, then I wanted to say that it doesn't know instead of making up some garbage. So let's check that too. So I'm just saying, what's my name? What happened here? Filter. I thought I'd set. Okay, probably did something wrong here. I'll have to debug. Like it should have set the filter to empty, but it's not doing that. Essentially, I was expecting it to just say, I don't know. Let's run that again. Okay, same thing. But you get the idea. That's pretty much all I had to show in the code walkthrough. Let's see. I'm going to go and see if there's any questions coming in. I think I can stop sharing my screen. Okay, cool. Yeah, if you have any questions so far, put them in the chat and let's go ahead and answer those. Okay. Someone's asking, is it possible to store images directly as vectors in MongoDB, or do we need to use a third-party tool or service for that? So you can store images directly in Mongo. You could either store references to the images. So say your images, raw images are in an S3 bucket. You could store links to the image, or you could embed the image using an image embedding model or a multimodal embedding model, and then store those embeddings in MongoDB. But just raw images is not something you can just dump into MongoDB. What else? Okay, I'm gonna just wait here for a little bit to see if there's any more questions coming in. Can we request a vector query from any driver, for example, Node.js? Yes, for sure. There's a few different drivers that we have: Node.js, Java, C Sharp, Python. So yeah, all drivers support vector search queries. Okay, I think there's no further questions. You can, of course, feel free to post any questions you might have after the fact in our community forums. You can reach me on LinkedIn. And yeah, if you enjoyed this session, we do live streams pretty much every week. So yeah, if you want to get notified about when we are coming on and future live streams, then you know the drill: like, share, and subscribe to our YouTube channel. Cool. I'm going to hop off. I'll see you next time.